All right, welcome back. Dr. P here. And in this lecture video, we will take a look at electrophilic aromatic substitution with substituted benzene derivatives. I actually want to go over a few things first. We're going to do I'm going to review the Friedel-Crafts alkylation and acylation first. And then we'll look at activating and deactivating substituents. And then after that, we'll look at other effects that substituents can have on these substituted benzene derivatives. Namely, they direct where the new, should be an O there, where the new group is going to go. So we could have ortho para. We could also have meta directing substituents. All right, so let's go ahead and go over the Friedel-Crafts reactions again. In part I'm doing this because I feel like I kind of squeezed them in towards the end of the last lecture video. I was trying not to go on for too long. You know how I like to go on. But there are some aspects of the Friedel-Crafts alkylation and acylation that relate directly to activating and deactivating substituents. So let's look at the Friedel-Crafts reactions again. So we'll look at the Friedel-Crafts alkylation. Remember, it works great if we have something like methyl chloride or ethyl chloride could work as well. We do have a problem, however, if we try to do this with a longer chain primary alkyl halide. So 1, 2, 3, Cl, AlCl3. So we do have some limitations. Since the electrophile is a carbocation, rearrangements are possible. They're not just possible, they're actually pretty likely if you have something where you can get a much more stable carbocation by doing a simple hydride shift. Another interesting thing is that the alkylated benzene derivative, so methylbenzene, which is called toluene, isopropylbenzene, which I think is called cumene, those are actually more reactive towards the Friedel-Crafts alkylation than benzene is. So you're actually making a more reactive product. So these reactions can be difficult to control. As you start making the methylbenzene, it would be more likely to react with the methyl chloride, aluminum chloride electrophile than benzene is. So once you start getting a lot of this, it can keep reacting with any excess methyl chloride that you might have, and you'd get a dimethylated or even a trimethylated species. So product is more reactive than starting material. So we would say that the reaction is difficult to control. And then the last limitation is that this only works on benzene, halobenzenes, or activated benzene derivatives. I'll just abbreviate derivatives there. All right, so these are our limitations. We can get rearrangements, the product is more reactive than the starting material, and it only works on benzene, halobenzenes, or activated benzene derivatives. And we'll talk more about activated versus deactivated benzene derivatives a little later on in this lecture. All right, let's take a look at the Friedel-Crafts acylation then. And we'll go ahead and add our acid chloride here. And we'll get our product. And because our electrophile is not a carbocation, we don't get rearrangements. Again, since we have this acylium carbocation, we're not going to get any rearrangements. Also, this acyl group is a deactivating group, so our product is less reactive than our starting material. So I'll write yay there and give it a little smiley face. So these overcome those first two limitations of the Friedel-Crafts alkylation. However, it still works, or it still only works on benzene, halobenzenes, and activated benzene derivatives. So we'll give a little frowny face there. So we still have that limitation. All right, now what do I mean when I say activated benzene derivatives? What do I mean when I say activating and deactivating groups? Well, let's take a look at this. All right. So an example of an activating group is methoxy. So if we had methoxybenzene, which is also called anisole, this reacts about 10,000 times faster than benzene. What should I say? Via nitration. So we would say that OCH3 is activating. Now, we could have something different. So NO2, so nitrobenzene, reacts about 100,000 times slower than benzene. Again, this is with nitration. So if we were trying to put a nitro group on methoxybenzene, it would be 10,000 times faster than doing it on benzene. If we tried to put a nitro group on nitrobenzene, it would be about 100,000 times slower than benzene. So we would then say that NO2 is deactivating. Okay, now question that you may be asking yourselves is, well, why is something like methoxy activating, but something like nitro deactivating? How can we determine what is activating and what is deactivating? Well, I will give you guys a table a little bit later on, and where we can see some general trends. But in order to fully understand what is activating and what is deactivating, we need to take a look at the mechanism of the reaction. So let's start by looking at activating groups. And these are also ortho, ortho para directing. All right. So activating groups are going to be electron donating, and they're going to stabilize the intermediate. So electron donating, they stabilize the intermediate. So it's going to give us a faster reaction. And the intermediates that give the ortho and para substituted products are more stable. So those are going to be the preferred products. So let's take a look at the actual mechanism here. So we're going to have our substituted benzene. I'm going to use methoxy. And again, I'll put in my hydrogens so we can keep track of the positive charges, because we're going to be drawing a bunch of resonance structures. And again, we'll have some kind of generic electrophile here. Okay, this is generic electrophile. All right, so we can go ahead now and have our, let me draw that a little bit better there, our pi electrons there pick up the electrophile. And let's go ahead and I'm going to have a bunch of resonance structures. Let me get this ready. So we'll still have that guy and that guy. We'll have an H there. We'll have an O, CH3, lone pair. We'll have an H, and we will have the electrophile. We'll have H, H, H. All right. So now I can go ahead and, whoops, I forgot my positive charge. So positive charge there. Okay. So I could go ahead and start drawing some resonance structures. So I could have the following. Double bond O, CH3. So positive charge on that oxygen. Still have those double bonds, still have electrophile and hydrogen there. Hydrogen, 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 hydrogen. All right, so let's go ahead maybe and let's see, let's push those electrons there and push those back up on there. And that will get me a third resonance structure. E, H, 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 positive charge. And then in this case, we've got a fourth resonance structure. All right, there we go. Okay, so we could have now our base, some kind of base, come along. So let's take our base here, and that's going to come along and deprotonate, and then we'll get those electrons going there. And that will ultimately get us now, let me draw it here. I'm not going to draw in all of the hydrogens here. But this is our ortho product. An ortho refers to the substitution pattern for our disubstituted benzene here. I've got substituents on carbons 1 and 2. So we'd say 1, 2 substituted. I'll just abbreviate that. All right. Now, let's take a look at what happens if instead we go ahead and have our electrophile picked up by these electrons there. And let's go ahead and let's see here. Yeah, we'll have those picked up. And Sorry, just making sure I get all of this right here. Let's go ahead and do that here. OCH3, H, and E, H, double bond, positive charge. So now I can go ahead and start pushing electrons around. I should probably remember my lone pairs on my OCH3 there. Positive charge. And now my final resonance structure. I've got the positive charge right there. So my base could come along and deprotonate, regenerating my benzene here and getting my final product. And this is the meta product. And meta is 1,3 substituted. Okay, carbon 1, 2, 3. All right. Now, there's a third possibility, and that is, what if our pi electrons here picked up our electrophile, and that's going to give us now, down here at the bottom, what if instead of the electrophile going here, our electrophile went to that carbon? That's going to end up giving us the para product. So we have H and electrophile, H, O, CH3. Let's see, H, we still have that double bond and that double bond. I got a positive charge there. I'll go ahead and draw in my little arrow there for my, move this up a little bit, there we go, for making my resonance structure. No double bond there, still have one there. E, H, still have H's there, there, and now a positive charge there. But I can go ahead and push electrons around. And that gives me now bond O, CH3, lone pair, positive charge. I have H, double bond, H, I have H, oops, I have E and H, sorry I switched them, but you know, erg, come on Wayne, H, double bond, alright. A lot of resonance structures to draw here if you want to fully show what's going on. So now I'll go ahead and push those electrons there and push those back up onto the oxygen, and that will give me my fourth resonance structure. And then, of course, I could have my base come along and deprotonate my hydrogen there, and I'll get my final product. And this is the para product, which is 1, 4 substituted. Okay, 1, 2, 3, 4. All right, so phew, quite a bit. Are you going to have to draw all of these? No, not necessarily. But you will have to draw the appropriate mechanism for what product you get. So, for example, if I ask you a question, you have this product, you need to draw all of these resonance structures. Now let's take a closer look at these resonance structures. I know that there's a lot here. What do we have? Well, for ortho and para, in this case, we've got 1, 2, 3, 4 resonance structures. We have additional delocalization onto the oxygen. We don't have that in meta. Okay, so ortho, 1, 2, 3, 4, para, 1, 2, 3, 4, positive charge on oxygen, positive charge on oxygen. Due to the substitution pattern, we can't get that positive charge delocalized onto the oxygen. So we don't have the same delocalization. Now, it turns out that something like an alkyl group is also activating because it has extra electron density on it that can help stabilize the positive charge. So if we had just a CH3 instead of an OCH3, we wouldn't be able to make that fourth resonance structure, but we'd have extra electron density that would help stabilize this guy there. And we just don't have that additional stability, that additional electron donating effect when we try to make the meta product. Okay, so we have more stable intermediates for ortho and para, so the reaction is faster. Faster reaction. Whoops, faster reaction. And again, the ortho and para products have intermediates that are more stable than the meta products intermediates. So those products are preferred compared to the meta. Phew. So we will see that activating groups are ortho and para directing. All right, so let me kind of leave that up here for you guys. Feel free to pause and you can copy this down. All right. Now, we also have deactivating groups. So let's take a look at a deactivating group. So the example that we saw was nitro. So let's go ahead and we'll take that here. And again, I'm going to try to squeeze this in. So if I have my electrophile, and I go ahead and grab that, such that I get, I'm going to draw out my NO2 here. Negative charge, positive charge, double bond O. And we'll have my H and my electrophile. And then I'll have my other double bonds, hydrogen, 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 hydrogen. Positive charge is right there. All right. Now I can push some electrons around. Let's push those guys over there. And that will give me, I'm just going to go back to calling this NO2. You'll see why in a minute. H, E, H, 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 positive charge, H. And then we'll go ahead and push those electrons around there and get the third resonance structure. So let's see, I still have that double bond. I push that one over there. So now my positive charge is there. And then I can have my base come along and deprotonate. And that gives me my ortho product here. Now notice that we have a positive charge next to the electron withdrawing group as we generate the ortho. Okay, so one of our resonance structures in our intermediate has that positive charge next to a nitrogen with a positive charge. And this could be another kind of electron withdrawing group, such as, say, a carbonyl. Remember when we made the Friedel-Crafts acylation product? So that carbon is electron poor. Actually go back and take a look. You can draw this to show it, but this carbon is electron poor. So in the intermediate, we're going to have a partial positive charge here, and when we, so if we're trying to, let's say, do a reaction with a, acetophenone, for example, we have an acetyl group there, we'll get a positive charge next to that partially positive carbon, and that would not be that stable. Okay, so this is kind of the key here. All right, we're destabilizing the intermediate by having that positive charge next to an electron withdrawing group. In this case, it's a nitrogen with a positive charge. So let's look at what happens if instead we go ahead and, I'll put my electrophile down here again. What if we go ahead and we make the meta? So I'm still going to have NO2. I'm going to have that. I'll have my H and my E there. Still have that double bond. Still have that hydrogen, so positive charge right there. So now I can go ahead and bloop, push electrons around. So I have NO2, still have that double bond there, still have a hydrogen there, 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 and there. I have my hydrogen and my electrophile that I've added. I have a double bond there, and now positive charges on that carbon. And now I can make my last resonance structure. And has a positive charge down there. And if I had my base, it can come along, deprotonate. And we'll go ahead and get my final product, NO2, E, boom, boom, boom. This is meta. Okay. Now notice that I don't have a positive charge in any of these resonance structures next to the electron withdrawing group. So let's go ahead and do it for the third case, which is our para case. Squeeze my my electrophile in there. Sorry about that. It's much easier when I've got a great big whiteboard to just extend across. I have an H there. Let's see, I have that guy there. That guy's there. I've added that there, so my positive charge is there. Now let's go ahead and push electrons, push those guys down there. Positive charge. Oh, we've got a positive charge next to our electron withdrawing group, so that's not going to be stable. And now I'll make my third resonance structure. Positive charge there. Of course, my base could come along. Oh, can't see my base. There's my base. It's all about the base. Base comes along, and actually in this reaction it's not all about the base, it's all about the electrophile and our deactivating substituent. Anyway, and this gives us our para product. Like the ortho product, we have a resonance structure that puts, this one here, that puts a positive charge next to the electron withdrawing group. And that is bad. So in all of these, we have an electron withdrawing group next to positive charge delocalized around the ring. So the reaction is going to be slower. But in the case of the meta substitution, its intermediate does not put the positive charge directly next to the NO2. Okay, we have that here with the ortho, and we have that here with the para. We have positive charge on the carbon that has the electron withdrawing deactivating group attached. So that's bad, bad. So our meta is our least bad. And that's why we get the meta product. So the reaction is still deactivated. It still proceeds, 100,000 times slower, for example. But the meta product is less bad. Getting, or I should say, making the meta product involves going through an intermediate that's less bad than making the ortho and para products. All right, one last thing to mention, and that is we have some types of groups, namely the halogens, actually it's just the halogens, that are deactivating, but they're ortho and para directing. So let me just take a quick look at that. So we'll say here halogens are deactivating ortho para directing. An exclamation point here. And why is that? Well, I'm not going to write out the whole mechanism, but if you want to, you can write out the whole mechanism. But we'll just say the following intermediate resonance structures are produced. Again, we have the other resonance structures as well, so you could draw all these out if you want. But because we have extra electron density, on the halogen, okay, it's electron withdrawing because it's electronegative, but it has lone pairs. So we could make the following intermediate, the following resonance structure. Same thing for para. Double bond there, double bond there. Same thing for para. So these resonance structures are stabilized by the lone pair, by a lone pair from the halogen. Okay, now you may be asking yourselves, well, isn't oxygen electronegative? Well, yeah, that's why if we had a CO double bond, like the, an acetyl group, an acyl group, that's why that ends up making a partial positive charge on the carbon, but not for this guy. Okay, we're happy with a positive charge on oxygen, reasonably. I mean, think about it, H3O plus, that's stable, right? But having a halogen with a positive charge, not so great. Yeah, we saw it in the bromonium ion when we do bromination of an alkene. But so these guys are a little more stable. So halogens will not be as deactivating as other deactivating groups, but they will be deactivating and ortho-para directing. Okay? All right. So next time, I think I'll sort of summarize this and show you different activating ortho-para directing groups. So, of course, the halogens are deactivating ortho-para and then deactivating meta-directing groups. So we'll take a look at those and take a look at some synthesis, and we'll go from there. All right. Well, thanks for sticking with me for the past 42.5 minutes, and until next time, stay safe out there. Bye now.